All right. So I went ahead and I would have worked out all of these things here, right? EVS rather. I worked out EVS. So this is what I came up with mainly when I did all of that stuff and all support. You can do it on your own to just verify just the same way. I mean, none of us are perfect. But of course, if you're going to plot the graph, right, you have to be a little bit specific as to what is happening. So on this axis, you wouldn't want to go up by, well, let me just say it. You wouldn't want to, you shouldn't write 0.1 and then put times 10 to the minus 19 beside of all these values. All you can simply do is to just factor out that and put it one side. So we will know that you're talking about zero point 0.1 times 10 to the minus 19. Same thing applies down here, so right? Same thing applies. So all we now need to do now is to just plot the points on the graph. So I believe the first point that we're looking at here is zero point 0.6 times 10 to the minus 19 to practically 5.5. So that would be somewhere about here. So right, just forgive me if my graph doesn't look as perfect because I mean I'm using a computer, but technically it would be somewhere here, right? But so right there. So then now the next value that we're looking at is 5.05 uh, to 0.3. So right about there, so right. Then now 4.9, right? The points are somewhat close to 2.5. All right, is that correct? Let me just check. Yeah, I think it's correct. I mean, the points are a little bit close. We have 4.9 again, but this is now 1 point, somewhere about here. I mean, I say it's not perfect. Then we have 7.7. That would be, I mean, 4.7 rather, 4.7 to 1. That would be right there. Now, they need us to draw a line of base fit. Now, the thing about these lines of base fit, they should really pass through the through the through the x-axis technically, because where it cuts the where the line cuts the x-axis, that is basically your corresponding to your threshold frequency. So right here, so right, that point is corresponding to your threshold frequency, which in this case is going to be about 4.5 times 10 to the 14 hertz. All right. So with that being said, we go back to the question. But prior to that, they want you to find Planck's constant, right? They want to find Planck's constant. So in essence, now you just need to pick 2 points on the line, right? And then just, so the point I'm going to pick is a point that I did not plot. So that's the first point. Then I'll pick this as my second point. All right. So we just want to prove Planck's constant mainly. All right. What you must understand is that the gradient for this is equal to Planck's constant. Okay. So what we're now seeing here is that y2 minus y1 divided by x2 minus x1. Let's see if we can identify the value here. So that's 0.52 times 10 to the minus 19 minus um, 0.15 times 10 to the minus 19. Divide that now by the x2 value. X2 value seems to be 5.5 times 10 to the 14th minus uh let me yes, so x1 now. That's going to be about 4.5, I believe, 4.7 rather, times 10 to the positive 14th. So calculators now. So we have 0.52 minus 0.15. Numerator, I get 0.37 times 10 to the minus 19. Divide that now by the denominator, basically. Let's find the difference. So 5.5 minus 4.2. 1 second here. Right? So we just need to just subtract that. Once we subtract that, I get 0.8 times 10 to the 14. Then all we just need to do now is to just put everything into the calculator. Alright, so based on this now, the values are, based on the values I get here, I get this, right? It's not completely close to Planck's constant. It's not completely close to Planck's constant, but that is what the graph is showing us, right? That is what the graph is showing us. So we're now going to go back over to this part. And I mean, if you see me doing anything wrong here, you can correct it or identify it. But I believe I did everything right for the most part. So we would have done that. So we get the value 4.6 times 10 to the minus 34 joules second. The reason why I know that this value is not inaccurate is because, of course, I have times 10 to the minus 34 times 10 to the minus 34, right? The question says we should calculate the work function. So psi is equal to Planck's constant times the threshold frequency. I recommend that you use the value that you got a while ago for the Planck's constant because you did an experiment mainly. So the 5.6 times 10 to the minus 34 times the value that we would have found out for the threshold frequency, which would have been 4.5 times 10 to the to the positive 14, right? So with that being said, 4.2 e to the minus 34, right, times 4.5 e to the 14, right? I'm getting that the work function has a value of 2.07 times 10 to the minus 19, and this is in joules. So I believe that would cater for that answer, right? Now, if you have a different work, you can let me know. Now the question continues here, right? Just to finish up this. They want us to find out what is P. I would say P is, that, we could say the incident electromagnetic radiation. Q, of course, we say that is the vacuum tube, right, are basically your photoelectrons. Reason why we call them photoelectrons is because they were liberated by light, photoelectrons. Now, there's another question here. It says that so the graph in figure 5, right, was obtained from a plot of stopping potential. So you can see this question now. It says stopping potential and not stopping potential energy. So that's a difference. So stopping potential, E uh, uh, Vs, right, against frequency, which is in hertz, obviously, of incident radiation in an experiment, as shown of an unknown metal. It says determine the slope of the graph in SI units. That's a 4-mark question. So we just want to find the slope. So we'll just pick a point here, right? And then we'll pick another easy point, which is here, right? So this is going to be now. We know the formula for gradient already. You need to state the formula. So state the formula, of course. Let's see. So that is what? 4 times, well, there's no times 10 to nothing. It's just 4. So that's 4. Let me just erase that. So 4 minus 1 divided by, and you must realize that there is a times 10 to the minus 4 down here, so, right? So let's see now. So the corresponding, that's 13, right, minus 6. All of this in bracket times 10 to the 14. Please put the bracket and put the value here. So for me, please don't work on the calculation, you calculate and just write down the answer. Don't do that, please. So we have 3 divided by 7 times 10 to the 14. So let's do that. We would get that the gradient m is equal to 4.28 times 10 to the 16, I believe, to the minus 16 or minus 15. My calculator is not showing me the exact value. They say they want a unit, right? They say they want a unit, SI unit. So let's see what unit we can come up with here. They want a unit. Wow. So we know that this is in volts, right? Frequency is hertz, right? I don't know if they want volts per hertz. I don't know if they want that, or they could want this joule second, because hertz is per second. So technically speaking, it could be VS, right? It could be VS. Yeah, I think it could be that as a unit. But if you have either one of those, I don't think they can give you completely incorrect. I mean, they said SI unit for frequency, I believe it's hertz, or it could be per second. SI unit for volt is is V, volt, right? But there are other units that you could come up with, but that is just going to take too much of the out of us, and we don't want to go through that. All right, it says with the aid of a diagram, with the aid rather of the graph in such and such, it says formulate an algebraic relation, relating rather the stopping potential, uh, to the frequency of the incident radiation. So this is where your equation comes into play. That says E, right, is equal to the work function plus the kinetic energy. right? As we would have pointed out, your kinetic energy is equal to EVS, right? Plus your work function, right, equals to, we know E in this case is equal to HF. So what I just simply need to do is to just transpose the equation. I'm going to make EVS become the subject. When I make EVS become the subject, I have HF minus my work function. I'm not completely through as yet. So what I need to do now is to divide both sides by E. When I do that, I get VS is equal to H divided by E F minus work function divided by E, right? So technically speaking, that is the equation mainly, right? That represents, you know, Vs and F. So this is your Y variable, as you can imagine. F is your X variable, right? Then what survives beside of it, that represents your gradient. It says, what does the slope of the graph represent? So technically speaking, M is equal to H divided by E, right? So that's what the slope represents, H divided by E. Not Planck's constant in this case, but H divided by E. It says, from the graph, determine the threshold wavelength of the unknown material. So what you must understand, threshold wavelength and threshold frequency, they are related to each other, right? Once you can identify your threshold frequency, then you can calculate your threshold wavelength. The threshold wavelength is simply talking about the maximum wavelength that the wave should have to cause photo emission, right? So one of the things you must remember here is this equation for the speed of light. C is equal to wavelength times frequency, right? You should now remember that, yeah. So once you go on the graph, right, you're gonna look for where the line cuts the x-axis. Based on this, it's going to be about 3 point. It's a 3.2, 3.2, 3.4, 3 point. Let's say 3.6. 3.6 times 10 to the 3.6 times 10 to the 14th, right? C, because we're dealing with light, that is 3 times 10 to the 8th. Then from there, so we just you know, from there, so we just go ahead and find the, from there, so we go ahead and we could find the threshold wavelength using this format. I'm trying to see if it values 4 marks that we're doing here. We don't know the work function, right? We could find the work function, but at the end of the day, it probably should give us back the same answer, because work function, as you can imagine, is equal to H times F naught. We can find F naught, right? So another formula that you'd see us using is that, you know, psi is equal to H, you know, times C divided by, you know, the wavelength, or, you know, wavelength naught. But because we don't really know what the what you call this now, the work function is, but we could find it if we want. You know, we could, because we know the speed of light has a set value, then we could just simply, you know, work out this thing from that. So 3 to the e to the 8 divide by 3.6 e to the 14, I am getting a wavelength that is about 8.33 times 10 to the minus 7 meters, which technically is saying 833 nanometers, right? So I will leave it at that for this particular question, right? You can go ahead and verify if that makes sense to you guys. Then of course you could go ahead and try this. We describe what is meant by photo emission. The same thing that we call cutoff wavelength is the same thing as what we call the threshold wavelength, right? So you could define that. You could derive an expression here, for the maximum speed of a photoelectron ejected. If you could go ahead and do that, and I think it will complete that there, all right?